So I am sharing the data file related to the case. We will run the regression analysis, then we would make interpretation. So this is the data file. Here we are having the dependent variable, that is the overall likeness. And we have 6 independent variable or 6 predictors: identity, visuals, youthfulness, superficial, connect, and image. You can check that this is the dependent variable likeliness on a scale of 1 to 7, right? It has been mentioned. Then we have 6 independent variables. All are metric in nature, right? As you check, the measures of all these variables are scale, right? And they are also on a scale of 1 to 7. And this is the complete description of the label. So I will share this data file, and we are having 200 cases, means sample size is 200. Now we will run the regression analysis. So we go to analyze, then we go to regression. And since we are going with the linear regression, so this will be our path. We will go to analyze, then regression, then we are having linear regression. So this is the dialog box of the linear regression. Here, space for the dependent variable is only for 1. So we have rebranded liking as the dependent variable, and we will select all these independent variables, and these variables have been entered in the independent box simultaneously. So this method is known as enter method. Enter method means all the independent variable, all the predictors have been entered simultaneously. This is not the only method. There are other methods also, like stepwise method, forward method, backward method, remove method. So these methods are known as sequential search. Forward and backward methods are software dependent, means software on in itself enter the variable as per their predictive contribution, as per their contribution, and in forward it is added, in backward it has been removed. And stepwise and remove method are the generalization of these two methods, where we can use different steps also. But since we are doing for the first time the regression analysis, so we are using the method enter, and all these variables have been entered simultaneously. Then we have statistics button. So this is the sub dialogs box of statistics. We have estimates and model fit. There is one more option, R square change. R square would be changed if you are using some sequential search method, or hierarchical regression, means forward method, backward method, stepwise method, or remove method. But we are not using. We also include descriptive statistics. We also have part and partial correlation, and we have collinearity diagnostic also. These things will be discussed when we are discussing the assumptions. Then we have Durbin-Watson also. So if you want to examine the impact of collinearity, you can also include case. Then we have plots. Plots are also being used to check certain assumptions that we will discuss during the analysis. So for the plots, here we have a scatter plot. So we entered Z residual. What do we mean by residual? I will explain. Z means standardized residual. I will explain what do we mean by residual. So Z residual has been entered in the Y, and Z predicted. I will also explain what do we mean by predicted variable or the predicted value, and Z being standardized value. So we enter Z predicted into X. We also have histogram and normality plots for standardized residual plots also. So we include this. All these things are required for assumptions checking. We continue, right? And if we put save, so save simply means the values are saved on the data sheet. So in order to explain predicted value and residual, we include predicted value unstandardized and residual unstandardized. You can include some other options also. In order to check the impact of different variables or outliers, you can include distances also. For the time being, we are ignoring it. So now I am having the output. So here, this is the output of the regression analysis. So first I should explain some concepts. Now, since you have taken y as beta 0 plus beta 1 x1 up to beta 6 x6 plus the error term. So this is known as our proposed regression model, and it would be for population. So this is known as population regression model. Since we are using a sample, here we are using a sample of size 200. So these values are estimated or these values are predicted. Right? So beta 0 is being estimated by B0. In the same manner, beta 1 is being estimated by B1 and so on. So we have an estimated value like y. It would be B0 plus B1 x1. All these B1, B2, B3, B6 are from the, they are predicted, estimated from sample. So these are the beta B values, right? And since we are using sample, so for sample everything is known. So here we are not having the extraneous term. So now if we substitute these values and for a particular case we put the values of x1, x2, x6, then we are having a value of y. So this value is being estimated for a sample by this value. So this value is known as estimated value or predicted value of y, right? And the difference of these values, y and y cap, this difference is known as error or residual. So error doesn't mean something went wrong. Actually, it gives the an estimate of epsilon or the error term. So they are known as residual values. So let me share the data sheet to show you these values, right? So here, for the first respondent have mentioned 4 on a scale of 1 to 7. For the likeliness, means this is the value of y, which is being provided by the respondent. So this is the observed value, and this is the predicted value. This value has been estimated or predicted by the model. So this is the predicted value, and it is the unstandardized predicted value as we have checked. And the difference between these two values is known as residual. So 4 minus 3.71846, it would be 2.8. Right? Now, suppose we are considering the second case. Here, the observed value of y is 2 and the predicted value is 2.76. So the difference is 2 minus 2.76. We are having minus 0.76152. So hope these two values are clear to you. Right? Okay. So now we are moving back to our board. Now we are performing the regression analysis. So what are the essential steps? Number one, we have introduced the problem. Since we have introduced the problem, means we have mentioned what is y, means what is the dependent variable and what are the independent variables x1, x2, x7, right? And why we are doing for this analysis. This has been introduction. So the problem has been introduced. The second is we would check assumptions. We would check the assumptions of the regression model. So when we perform the analysis, I first introduce the assumptions, but we will check later on. We will check the assumptions. Then we check what is the whether the model is significant or not. We examine significance of the model. What do we mean by the significance of the model? Means whether there is significant associative relationship between y and x1, x2, x6. Means these combination or this linear combination is known as regression variant. So first we examine whether the model is significant or not. So this is known as overall significance of the model. This is known as overall significance of the model. Means model, whether the model is overall significant or not. So here, obviously, there may be two answers of this significance. Answer may be yes, answer may be no. So if answer is yes, we will move forward. If answer is yes, we will move forward. Right? If answer is no, means model comes out to be insignificant. So there may be some reasons. The first reason may be, suppose we have mentioned the wrong functional form. What do we mean by wrong functional form? We have assumed that this model is linear. It might be possible that this relationship might not be linear. It may be non-linear. Means we have, instead of linear regression, we should use non-linear regression. So one reason is we have mentioned the wrong functional form. So we would check whether this is correct or not. Right? Again, the second reason may be we should consider some other predictors. Right? Means these predictors are not substantial, not important, and since there are n number of other predictors, n number of other variables also, so there may be some other reasons which are having an impact on y. So we have to look for these two cases if model comes out to be insignificant. Suppose this model comes out to be significant. Then we move to examining strength of the regression model. Then the fourth step would be strength of the regression model. Why strength is being examined? To check whether it has high predictive accuracy or not. Right? We would check whether it has high predictive accuracy or not. So far, these two things are related to overall model. Now we move to individual part. So our fifth step would be we examine significance of predictors or independent variable. Means here we are having 6 independent variable or 6 predictor. So all 6 may be important, all 6 may be significant for the relationship, and it might also be possible that not all 6, 3, 4, 5 are only significant. Means they are having an impact. It is just like the when we have relationship in the real life, then it is not necessary that everything is get affected. Right? Means everything is important. All the 36 properties should not be matched. Even if even then we will have relationship. So this is the concept that we examine whether what are the significant predictors, right? And then we also create hierarchy of significant predictor. We also create hierarchy of significant predictors. Means if we have more than one significant predictor, then obviously we must be interested which one is having the highest relationship, or which one is most important in this associative relationship. So we create a hierarchy of significant predictors. And the last step would be we propose the regression model. So this regression model is proposed for the prediction purpose, for the future purpose. So these are the steps. One has been done. These are the steps that we are going for the analysis. So first I will tell you about the assumptions, and assumptions checking would be done towards the end. Okay. But when you write the research paper, then obviously assumptions should be discussed forehand only. Right? So these are the assumptions. These are the slides. So what is the first assumption? There should be linearity of the phenomena. I mean, there should be linearity in the regression parameter. So how the linearity can be checked? We can use scatter plot. Right? Scatter plots are available even in Excel also. So we have independent variable on the x-axis and the dependent variable on the y-axis. If points lie on a straight line, means there is linearity. Second assumption is independent variable is deterministic in nature. So we have all xi's are independent. Next is there should not be high correlation between independent variables. Means x1, x2, x6 should not be highly correlated. Otherwise, there is a problem of multicorrelate. We will discuss in detail the problem related to multicorrelate. Multicorrelate means there is high correlation, there is substantial correlation between independent variables. Now, in regression analysis, actually there should be correlation between y and the independent variables only, but there should not be intra-correlation between independent variables. So there should not be multicolority. So this is the assumptions. This assumptions is related to predictors or independent variables. Now we have some very important assumptions related to error term or the residual term. So these assumptions can be written in one line also. So I should write the first line that this error term or epsilon should be identically independently distributed normal variate with common mean 0 and common variance sigma square. Right? Let me explain. That error term is I. I means identically, means all are same. Second I is independently distributed normal variate. Right? This is a random variable. As we know, we have discussed that this epsilon or error term is random variable. So this is a random variable. So it will follow a probability distribution. This probability distribution is normal. And for normal, we require two things that I have discussed in the previous lecture also, mean and variance, right? So the mean would be 0 and variance should be constant. This variance is constant. Identically and independently distributed normal variate with common mean 0. All means will be 0 and common variance as sigma square. E is the suffix, means it denotes the variance for E. So these lines are detailed in these 4 points. Number one, residual should follow normal distribution that we have discussed. And if there is normality, a non-normality, it is because of misspecification. Misspecification means we have chosen wrong functional form, right? So if there is non-normality, means errors or residual terms are not following normal distribution, means there we are using wrong functional form. Means suppose the relationship may be non-linear or it may be exponential, but we are using linear regression. Next is conditional expected value. Conditional expected value means mean. Mean of the error term is 0. It has been mentioned. And residuals are independent. They are uncorrelated. Means correlation between all the error term epsilon 1, epsilon 2, and so on would be 0. They are uncorrelated. Otherwise, there is a problem known as autocorrelation. So if they are not independent, then there will be a problem of autocorrelation. We will discuss in detail. The last one is all variance terms are same, all variance are constant. If this is so, then we can say that variances are homoscedastic. Homoscedastic means common variance. Otherwise, there is a problem known as heteroscedasticity. There is a problem. Heteroscedasticity means variances of the error terms are different. And if these assumptions are fulfilled, then we can have the estimation. So these are the assumptions that are required for ordinary. O stands for ordinary. L stands for least square estimation, right? So this LS stands for least square. So this is the ordinary least square estimation. So if these assumptions has been fulfilled, then we can employ ordinary least square estimation. And if ordinary least square estimation is used, then this model is known as classical. C stands for classical. L stands for linear. R stands for regression. And M stands for model. And through this model, we have blue estimator. Blue means best, means having minimum variance. So best prediction would be done. Most authentic prediction would be done. L stands for linear. U stands for unbiased. And E stands for estimation. So we have best, linear, unbiased estimation, right? So these are the assumptions. If these assumptions has been fulfilled, then this method, application of this estimation method is justified. As you see, we have checked these assumptions that we will discuss towards the end. So these are the assumptions that we will discuss towards the end. Right? So for the time being, I am ignoring this, right? We will discuss towards the end. And as in this model, first I would discuss significance of the regression model, right? Right. Then we move forward, and then in the end we will discuss the assumptions, right? So we are checking significance of the proposed regression model, right? So what do we mean by significance? Since we have data from sample and we want this model for the totality for the population. So we want to check whether the results which are evident in the sample are significant for the population or not, right? So this is the objective of checking significance of the regression model. Since we have data from the sample, we have data from a sample of size 200. We have analyzed this data and estimated this model from the sample values. And we want to apply this model, right? We want to apply this model for decision making for the entire totality of the entire population. So we check whether this the results that are obtained from the sample are significant in the population or not. So this significance of the regression model is done by proposing H naught. And since here we propose H naught as, since H naught assumes no difference, so we proposed H naught as regression model is insignificant. Means on a rustic language, we can say that regression model is zero. So regression model is insignificant. So regression model is insignificant means R square. We would discuss what do we mean by R square. R square would be zero. R square would be insignificant. And all coefficients, right? All coefficients beta 0, beta 1, beta 2 or beta 6 would also be 0. Means there is no significant regression coefficient. So we will examine this H naught, and obviously H1 would be opposite to this. So first I will explain the concept of this analysis. So let me show you the data file. So if you observe the data file and you observe the values of likeliness, which is our dependent variable, rebranded liking. This is our dependent variable. So if you observe these values, we have 4, 2, 6, 5, 4, 4, 7, 2, 6. Means there is variation among these values. So we would consider this variation. Means there is variation among these values. So we can say that we have variation. So we are considering total variation or total sum of square in Y. Right? So we have total variation. or total variation or total sum of square. Both sum of square is also an indication of the variation. So now we examine what are the reasons of this variation. One reason is because, let me share the data file again. Okay. As you see, here we are having value 4, here we are having value 2. So one reason may be that the respondents or customer are giving different values to independent variable. So because of change of these values, value of y may get changed. Right? In the same manner, as you observe, these values are also changing. So because of changing or change of these variables, this y may change. Right? So one reason can be with change of x1, x2, x6, the y may change. Right? It has been visualized in the model also. Since it has been visualized in the model, so that's why we are performing the regression analysis. So this reason is known as explained regression or explained variation. We should write it as explained variation. This is the explained variation. Means we know the reason of this variation, or this is the variation because of regression, right? Because of the regression model. Because in this model, we have assumed that these independent variables, these predictors are related to y. So if these x1, x2, x6 are changes, these x's are changes, then y would also change. So this variation is explained. And we also know this y maybe get affected by some other variables which are not included in the model. So that variation is known as unexplained variation. Why unexplained variation? Because we are not considering that variation in the model, which basically represents the error term. They are basically because of the extraneous reasons, error, right? And they are also termed as because of residual. Residual means they are beyond the model, they are different, they are separated from the model. So the total variation may be bifurcated into explained variation and unexplained variation. Since again we are considering variation, so this concept is known as analysis of variation or ANOVA. Means we are considering analysis of right? We are considering analysis of variance. Okay, right? So this is the total variation. Suppose this explained variation is very high. So if explained variation is high, so obviously unexplained variation would be low, means much of the variation is because of the regression model. Then you can say we are having a good or substantial regression model. So we can say that regression model is substantial or regression model is significant. Right? Now we consider the ratio of these two variations. So suppose we are considering the variance ratio of explained variation or variation because of regression in the numerator and unexplained variation in the denominator. And unexplained variation that is residual in the denominator. Okay, right? So now in this case, if explained variation is much higher as compared to unexplained variation, so value of f would be much higher as compared to 1. So we are having a big f value. And since this f is an statistic or the test statistic, it will follow f distribution or the variance ratio distribution, as I have discussed in parametric testing also when we are considering the ANOVA. So this is the sampling distribution or probability distribution of f statistic. Right? Here we have probability of f, and here we are having f value. It can never be negative since we are having sum of square of variation in numerator as well as denominator. This mode or the highest frequency would be at 1. So as we move, as the value of f is higher than much higher than 1, we are getting a big value of f. So if we consider the corresponding right tail probability or the p value, which is denoted by significance, right? So now we are moving back to this. So if we are getting very high value of f, or f is much higher as compared to 1, then again we can say that our regression model is significant, right? So if f value is high, then obviously the significance of the p value would be low, right? And suppose this is less than 0.05, so we would reject. We have proposed regression model is insignificant. It has been rejected. So we can say that our proposed regression model is significant, right? So this is the explanation. So if this is not the case, if if explained variation is not much higher as compared to unexplained variation, means they are approximately equal, then value of f would be near about 1, and correspondingly we have a high p value. And if we have a high p value and the p value of significance is greater than 0.05, so we cannot reject h naught. Since we cannot reject h naught, then we have to say that our proposed regression model is insignificant. Now I am sharing um, the output for the interpretation. So this is the output. This is the first table which gives the descriptive values. It gives the correlation among different values. We will discuss when we are discussing the assumptions. It tells us about the method that we have used. The method is enter method. Dependent variable is rebranded liking, and these are the independent variables, and all these variables are entered simultaneously, right? Now, as I have explained, we are considering the significance of the regression model, and it has been discussed by bifurcating the total variation into the two parts. One is explained variation, that is regression, and other is unexplained, that is residual. So here total sum of square is being bifurcated, total variation has been bifurcated into these two parts, right? And here we have the formula for the variance. Mean square is simply sum of square divided by degrees of freedom. It will be 5778.866 divided by 6. We are getting 96.311. Here we have 202.287 divided by 193. We have mean square. We are having mean square or the variance as 1.018. So as you observe, variance because of regression is 96, and variance because of residual or the error term or the unexplained variance is just 1.08. Right? So 96 is much higher as compared to 1, as we have discussed. And f is the ratio of explained variance upon unexplained variance. Means it is the ratio of 96.311 divided by 1.048. So we are getting a high f value, that is 91.89, and correspondingly we are having a low p value or low significance as 0.001, and this p value is less than 0.05. So we reject h naught, and we can say that our proposed regression model is significant. Means these 6 predictors or this regression variant as a linear combination of these predictors is significantly associated with rebranded liking. So let us write the result. We are having f as 92. So here we can write, here we have f as 91.89 or 92. This is a high value, and the p value of f is low. This is 0.000. This is less than 0.05. Right? This is less than 0.05. So we would reject h naught. So we can say that our proposed regression model is significant. Now you can make some practical explanation of this result, that regression model is significant. So this is the first thing that we have discussed. Right? So this is the actually this step has been taken care of. That is the significance of the regression model. Let us explain the second part also. Now the next part is we are examining the strength of the regression model. Or we are checking the predictive accuracy of the regression model, right? So we have discussed this bifurcation of the total variation into these two parts. So here we propose R square. R square is actually known as coefficient of determination. This R square is the ratio of explained variation right, or sum of square because of regression as per the ANOVA table divided by total variation. So this is the total variation TSS. Right? Let me show you the output. Right? Here we have SSR as 577.868. So it will be in the numerator. And the total sum of square is 780.155. So we divide 577 divided by 78T. Right? If we divide, then we are getting a value of 0.741. So this is the R square. Right? So let us discuss this value. This is the R square. Right? Now this R square is the ratio of sum of square or variance. So it can never be negative. So it should be greater than or equals to 0. We should have some space. Right? This is known as coefficient of determination. Right? So this value will always be greater than 0. And since explained variation is always a part of the total variation, so explained variation can never be greater than total variation. The numerator can never be greater than the denominator. At most, explained variation would be equals to the total variation. Means numerator can be at most equals to the denominator. So the maximum value is 1. Right? Now we discuss some values of R square. Suppose R square comes out to be 0.90. So 0.90 can be written as 90 upon 100. So if we compare with this, so what we have? So if the total variation is 100, then out of the total variation, the explained variation is 90%. Means here, our model is being able to explain 90% of the total variation in Y. Means our proposed model is being able to interpret, able to explain, able to take care of the most of the variation in Y. So obviously, if this is the case, then you can say that this model is strong. So we can say this model is strong. Means if we are having values of R square near to 1, then we can say that our proposed regression model is having high predictive accuracy, or is our regression model is strong. So if values are near to 1, then we can say that this relationship is strong. Right? Suppose we take one more case. Suppose R square is 0.15. 0.15 means 15 upon 100. 15 upon 100 means if the total variation is 100, then the explained variation part is just 15 or 15%. Means our model is able to explain only 15% of the total variation. Means most of the variation is being explained by the residual or the error term. Means they are extraneous to the model. So if this is the case, then we can say that our model is not so strong. So it gives the impression of a strong model, or highly accurate model, and it gives the impression of a weak or not so accurate model. So if values of R square is near to 0, then we can say that we are having a weak model. In our case, R square is 0.73. Let me show you this value again. So here R square is, sorry, R square is 0.741. Adjusted R square is 0.73. Right? So here R square is actually 0.74. 0.74 means it is having a predictive accuracy of 74%, or our proposed model is able to interpret, able to explain 74% of the explained variation. So we can say that our proposed model is good or proposed model is strong. So this is R square, right? So this is the concept of R square. Now actually R square is being affected by two terms. Is being affected by number one, size of sample. Size of sample means that is N, right? So the concept is if N is small, means size of sample is small, right? Then value of R square got inflated. Value of R square increases. So if we have a small sample size, then R square got inflated, value of R square becomes very high. So R square is affected by the size of the sample, plus R square is also affected by number of independent variables or number of predictors. They are denoted by K, right? So number of predictors means if K is large, so R square being a non-decreasing function, so if number of predictors, number of independent variables are large, then R square again got inflated. Means if we have a big model, if we have a number of independent variables, then R square will also be high. So these are the two weaknesses of R square. So this R square is normalized with respect to size of sample and number of predictors, and accordingly we have a better measure known as adjusted R square. So this R square is being adjusted with respect to the size of sample and number of predictors, right? So we are using adjusted R square. Actually adjusted R square is the ratio of mean sum of square because of regression divided by mean by total mean square, right? Okay, means we taken care of these two values. So we have a better measure of adjusted R square. In this case, we have adjusted R square as 0.73. Let me show you the output. Right? Yeah, we have adjusted R square is 0.733. Right? So we are having adjusted R square is 0.73. Right? So again, it gives 73%, 73% again gives the impression of a strong model. So as you see, here we are having R square as 0.74 and adjusted R square is 0.73. If you observe, then there is not much of the difference. So what is the reason of not much of the difference? There are two reasons. Number one, our N is 200, right? Which is much higher as compared to the uh, sample size that is required as per the thumb rule, that is 20 times number of predictors. So it is much higher as compared to 120, and here we are having only 6 predictors. So since already N is very large and K is small, so these are not having much of the impact. So that's why there is not much of the reason. So you can use any of these two values, right? So this is the explanation of R square. We have some more term. We have We have a term R. R is known as multiple correlation coefficient between observed value of y, that is y, and estimated or predicted value of y, that is y cap. So here we are having value of R, or multiple correlation coefficient. Right? Let me have this value from the output. So this R, this is the multiple correlation coefficient. This R is simply the square root of R square. So if we do square root of 0.741, we are getting a value of 0.861. So here we are getting a value of 0.861. This is 0.861. This value of R, or multiple correlation coefficient, lies in between 1 and 0. Right? Okay, so this is again closer to 1. So we can say we have a strong relationship. Right? There is one more term. Let me explain that term also. This is a standard error of estimate. Standard error of estimate is simply the square root of MSE. Means it is the square root of 1.048. So we are getting a value of 1.024. It gives the variation with respect to the regression line. Right? So let me explain it. Suppose this is the regression line. And the values are this one. Right? So as we see that there is not much of the variation, means the standard error or standard deviation of these values would be low. So here we are having a low value of standard error, means which is measuring variation of the points with respect to line. Suppose in some other case, points are so scattered, right? So here much of the variation means standard error would be low. So for a good model, standard error would be low. So this is the value of standard error. This is I am showing. This is the value of standard error. So we have discussed these two things.